Okay, the step is that we have to perform this KVL analysis based on the phases that happen in the circuit. So since that this source is in sine wave, so we have to bear in mind that we have a positive cycle, then followed by the negative cycle. Then it repeats itself, positive, negative, and so on. So one cycle consists of 2 pi, and pi here, positive cycle. Then from pi to 2 pi is the negative cycle. So the steps that from the circuit, we have to understand in terms of their equivalent circuit response. Positive cycle, and phase 2 is negative cycle. Positive cycle, negative cycle. Then during the phases, what are the conditions? What are the event or behavior or the parameter involved during that condition? Okay, equivalent circuit during first half cycle, positive cycle, is this one. Means that during this phase, the Vs in the positive pole here, positive, negative pole. Okay, during positive pole, the diode is forward bias. So actually we have diode here. So there is a diode here, drawing on diode. But during the positive forward bias of the diode considered as which is considered as an ideal switch. It will be open, it will be short circuit, purely short circuit, means that it will be conducting the current, and the whole current is conducted. By that, the practical diode, there will be a resistance, and resistance over voltage, whereby there is losses, there is a voltage drop. But ideally, there will be considered as pure connection with the zero voltage drop, with pure, or the current is flowing through the circuit as a short circuit. The circuit shorted. So this is forward bias. So during forward bias, what happened? V across your diode, V drop across the diode is 0. And you can see that the condition here, equivalent circuit and condition. The condition is that this kind of positive cycles happen from 0 to pi. Happen from 0 to pi, and here. Okay. Then V across D, and V across D here is 0, because V is equal to IR. And when we have a zero resistance at the D, zero resistance, so the resistance is 0, so V equal to I times 0, which is 0. So VD is 0. And some more, the voltage across your output here. If you measure voltage across output, voltage across input, and so voltage across output here, V out, is equal to Vs, because we have a short circuit over here, short circuit. So means that the terminal here and the terminal at the load is the same terminal. So V out is equal to Vs. How about the parameter of the current that flows through from source to load? So I equal to V over R. So means that if you want to measure the current that flows through R at the load terminal, so V out is here, divide by R. So V out and Vs is the same. So I equal to VR over R ataupun, or V out over R, also the same. So this is the amount of I. So from all the values here, the condition of positive cycle, we can plot the waveform. So this is your V in, this is your V out and I out, this is your the response of your VD. is that this happen, or you can read, when we measure the voltage across our device here, VD, and voltage across device, and VD over here. The VD is here, we cross the diode. Okay, practically we can draw the shape based on phase from 0 to pi here on the V source, and on the V out, how much we have the peak value, the shape. Actually, at this point we have idea on how to draw the shape of the waveform. Let's say the VD is 0, from 0 to pi. VD is 0, V out is equal to Vs, V out is equal to Vs. So parameters of V out here, same as Vs, and I is equal to Vs over R. So we have here I. Okay, this is for positive cycle. Then next on the phase 2, which is negative cycle. Just now it's positive, negative cycle. So for negative cycle, you have to redraw this circuit again, because this circuit we have a bit mistake here. So we have to redraw again. Okay, actually when the negative cycle taken place, negative cycle, so Vs is no more on positive mode but on the negative mode. Means that Vs is conducting on the reverse side here. So we have to delete the nothing here. So means that the current is flowing to the load back to the source upper side. So not this mark lah, you have to change. So positive, negative, positive and negative. It's not the original nothing. So positive, negative, positive, negative. The KVL, if you start from Vs, so negative Vs, positive VR or V out, positive VD is equal to 0. Again, you can rewrite Vs equal to V out plus VD, the same like the above statement. KVL, Vs equal to V out plus VD. But now this is on the negative cycle, so the current flows upward, anti-clockwise. So the clockwise you have to delete now, you have to cancel. Okay, this is the thing happened inside the second phase. So what happened here is that on the condition point of view, this cycle happened from pi to 2 pi. So this is the negative cycle. And at this time, the diode is on the reverse bias. So when the diode is reverse bias, it behaves like an open circuit, and it behaves like open circuit. So no more considered as short circuit like the forward bias, but it is an open circuit. So we can represent for analysis the diode to be like an open circuit. We can open the circuit. So what happened here is that there is no current, so I is equal to 0 because the open circuit, the loop is open. V out is equal to 0. You can see that V out is equal to I out times R out. The I is 0, so V equal to 0. V out is 0. Okay. And all the supplying source voltage then deliver to the diode. That's why we have a VD equal to Vs and VD equal to Vs, but this is negative on the negative point. That's why we can draw during negative cycle, the I is 0, so I here is 0, this I is 0, V out also 0, and V out 0, 0, and V diode, the V diode here, we follow the V source, but on the negative phase as well. So we can draw, means that this is the analysis that we can perform for phase 1 just now, positive cycle. The response is that the V out we have here, I out, and V across D is 0. Then for the negative cycle, V out 0, I 0, but VD, V diode, we follow the V source, but on the negative side as well. So it repeats again on the next full cycle. Next full cycle, it repeats again. So it means that when you presenting your result, you can use this kind of step. You draw the circuit, equivalent circuit on the phases, positive and negative cycles. Do you know what is the condition at these phases, and then draw the circuit, draw the waveform, the responded or the corresponding waveform. Okay. Means that here we have V out, V in, the input, then the output, and the device response. Okay. Okay, on the above slide, we have discussed on how to sketch the output, but for quantitative values, is that what are the exact value that the parameter contain. So can be represent or can be calculated by the mathematical equation here. So we have understood that the source is sinusoidal, so the representing sinusoidal equation is Vs here is equal to V max sine omega t. V max sine omega t. So we are able to calculate what are the average and output, RMS voltage, then the current and the power. All three parameters of voltage, current and power can be calculated by this equation. So if you refer to your textbook, you can find this in page 37. Page 37 in your textbook. Okay. And how to derive the equation. So in general, for V out, and V out, if we measure instantaneous V out, so this is the pattern. This is the pattern. But when we measure using a scope or using a multimeter, so we are measuring the average output and average output, or we are measuring the RMS output. Maybe you use multimeter, so it will measure the average and RMS. But this kind of measurement in terms of peak, you can only measure using scope, oscilloscope, probe, and which shows the instantaneous response of the system. But mathematically, we can calculate in terms of their average output and RMS output. So V output in terms of your average values, you will integrate between 0 to pi here, from 0 to pi, and you will get the values of 0.318 volt. Vm is maximum value times 3.318. So this is average output of your voltage. Meanwhile, your RMS voltage, so will be finally Vm divided by 2, and half of Vm is your RMS voltage. This is applicable only for your uncontrolled half-wave rectifier. Uncontrolled half-wave rectifier. So from RMS voltage, you can obtain your from your voltage of RMS and average, you can obtain your output current in terms of average and also RMS values when you divide with R, the resistive element. V average divided by R, so you will get RMS current, average current. V RMS by R, you will get your RMS current, average and RMS, which is also equal to V max divided by pi R.